What I'd like to do today is just give you an overview of what all we're going to be covering this semester so you can kind of see how it all pieces together, where we're headed. In Calc 1, you should have wrapped up just learning about integration, this idea of reversing differentiation. And so what we're going to start off with is to give some motivation to why you would want to do integration. So we will start off with applications. So integration, first we'll look at some applications. You saw a little bit already that there's a relationship to integration in area, and we will expand on that to volume, surface areas, lengths, other geometric features. But then we'll also apply it to some concepts in physics. It's more than just area under the curve. Any sort of summing process is going to be related to integration. So we'll start with the applications so you can kind of get an idea of why you would want to integrate in the first place. And then after that, you learned that from the fundamental theorem of calculus, to evaluate a definite integral, you just take the antiderivative and evaluate it at b and evaluate it at a. Well, that sounds simple enough, but how do you figure out what the antiderivative is? You've looked at some simple cases already where you have something that you recognize as the derivative of something else, like 2x is the derivative of x squared. But as the forms get more complicated, we're going to need approaches that allow us to rewrite things in ways that we can recognize. So the next big chunk is going to be these techniques. How are we going to take complicated functions and find their antiderivatives? And then closely related to that is what are called series. And if you think about an integral is a summing, right? If you think about the Riemann sum, you've got these rectangles, right? And we shrink them down. They get skinnier and skinnier, and we add up all those areas. So integration in itself is a summing. It's a continuous summing, if you like. It's over a function that's defined over an entire interval of real numbers. If you're just looking at a discrete sum, so imagine a list of numbers being added up forever, that's what a series is. So we'll start off in looking at the idea of convergence. Now, if you have a sum of numbers, we know that you can always add those up, but what if there's infinitely many numbers being added up? Well, there's no guarantee that when you add up infinitely many numbers, you're going to actually approach some total. So a lot of what we'll be doing in here is determining whether or not there actually is a sum. So we will look at techniques for taking a series and figuring out, does that series actually add up to something or not? Sometimes they'll converge, sometimes they will diverge, meaning they don't add up to anything. So we'll spend some time looking at convergence and divergence of series. And then we will transition into using those series. What are series for? What are these infinite sums? Well, we will look at functions. So the good old functions you know from algebra, specifically what are called transcendental functions, as series. You may not have thought about this before, but functions like sine and cosine, those trig functions, and functions like natural log, e to the x, those are what we call transcendental functions. There is no formula that can tell you how to calculate those things. That's what makes them transcendental. So that's a problem for us. How do you calculate something that has no formula? Well, one way to do it is to write it as an infinite sum. Now, you still can't calculate that because it's infinite, but you could take some partial sum of that as an approximation. So this idea of rewriting a function as a series is sort of the goal of all this convergence and divergence talk there. So we'll spend some time there in series. And you can also, we'll also look at using, kind of bringing it full circle there, we'll also use these to approximate integrals. So there is a connection. we'll kind of end up back at integrals in series. So in situations up here where these techniques aren't good enough, not everything has an antiderivative. So the idea of doing an integral by finding an antiderivative is not always possible. So you learned some approximation techniques in Calc 1, rectangles or trapezoids or Simpson's rule. This is another way to go about it, to write it as a series. And then the last bit, the third section, is what I think of as transition. We're looking at some topics that'll get you ready for Calc 3. The first thing we'll look at is what are called parametric equations. And these are a different way of writing the equation of a curve. And the nice thing about these parametric equations is they allow us to model motion, which is something we can't do with our good old Cartesian equations. They also allow us to move into 3 dimensions, which, remember, Calc 3 is really Calc 1 and 2, but in multi-dimension, 3, 4, 5 dimensions, more variables. So the idea of finding an equation in 3D is something that we'll be able to do in parametric equations. And then lastly, we'll look at a different coordinate system called polar coordinates. And the polar coordinates will be a basis for a 3-dimensional coordinate system you'll look at in Calc 3 called cylindrical coordinates, and also another coordinate system called spherical coordinates. So this helps us transition out of 2D into 3D with a new coordinate system. This coordinate system, instead of measuring x's and y's, it measures angles and distances. So these last 2 topics will be sort of a preparatory, getting us ready for some foundational stuff to get into multivariable calculus. So I would say, as chunks, this is probably 40%, 40%, and 20%. This last bit, the transition stuff, is a smaller bit of what we're doing. The main thrust of the course will be doing integration and determining convergence and divergence of series. So as we begin, make sure you know your differentiation rules. If we're going to be trying to do things backwards, integrating, finding antiderivatives, you need to know those differentiation rules perfectly, right? And also, one thing that I think a lot of people are weak in, because maybe it's been a little while, is the trig function. So make sure you know the common identities and the common values of trig functions as you start to get ready for this semester. Having a lack of that prerequisite knowledge can sometimes be a stumbling block. So let's make sure we're good on our algebra and our trig. So have a good semester, and I'll see you in the next video.